Shall I start? Shall I wait for 2 more minutes? All of you?
Yes,
yeah.
Sir.
Okay, fine. I'll start. So, what I planned is just to give you an overview or just a revision of the topics, because anyway we had a lengthy discussion during regular class, and I kept you busy till that internal finalization marks. You had 9 e-quizzes plus tests and assignments also. So most of you are aware of the topics anyway, and I have gone through it. So it's better to just highlight what is important for exam, and recalling important concepts. Okay, because anyway this is quite lengthy. Anyway, we cannot cover all the topics. So I'll go through the topics. Okay. So objectives and all I have shown you. Okay, not of any use. So syllabus is basically in the first module we learn about the key enablers for LTE and wireless fundamentals, and second module multi-carrier modulation and other related stuff. So anyway, your exams are open choice, so that means 5 questions. Any 5 questions you can answer out of 10. So there is no restriction on modules and which one to pick, and also any choice you can do. So I advise you to not go in depth of module 2, because it's of 3 chapters in textbook and it's quite lengthy and somewhat difficult also. So it's better to concentrate on module 1, 3 and 5, which I did in class, and I'll just do a quick overview of module 4, which is module 4 is basically similar to module 3. So these 4 modules, or any 3 modules out of this, are 1, 3 and 5. If you study, I think is good enough for final exam. Okay, it's up to you anyway. So these things I can give it a skip. So these are the just recalling the concepts. This is the terminology that we used till we arrived at LTE architecture or 4G architecture. So this is just to get to know about the things. The area served by the cell, served by the mobile tower, which is a base station, is called a cell. So base station is a mobile tower, and that terminology has been changed to E node D in LTE. Okay, and mobile users attached to network through base station, and air interface is the physical and link layer protocol between the mobile and the base station. Okay, so the frequencies, the power control, all these things come under the air interface thing. And these mobile towers in group are connected to MSC, mobile switching center, and this is all belong to a particular mobile service provider, and that is connected to a PSTN, public switch telephone network or internet. So whatever the external link you have, external connectivity you want outside the network is provided through that. Okay, so that is a wired network. Till mobile switching station, till in some cases till base station it is wired. After that it will be wireless. Okay, so these are the few fundamental things before we start the actual topic. So this is how the technology progressed from 1980s, when we had the first mobile, as we know today, phone existed. Not talking with 125 users in Stockholm in Sweden, and then they developed a technology, and by 1990s, just before 1990s, we had 1G technology, which was a TACS, Access Communication Systems in UK. And then by 1990s, 91, we started the development of 2G phones, and by development and implementation of 2G, and by 2000, we had 2G network all over the world. Okay, and 1G network almost non-existent by then. And then by 2000, uh, and after we had this development of 3G and the implementation of 3G, and still we have this 2G, 3G in existence along with 4G. And after 2010, we had this 4G network and its implementation worldwide. And now 2020 and beyond, we will see the 5G. Okay, this is how the mobile technology evolved. So you can see this figure, research and standardization and commercialization phases are given as per the legend given on the bottom left. So these are the things about 1G to 4G. So 1G was basically voice only, analog cellular phone. Voice was non-digitized. Voice was sent as it is, and the signaling was digital in 1G. 2G changed all that. 2G, everything was digital. Even your voice in a 2G is more digitized and then transmitted. And then 2G provided scope for little bit of data transfer. 1G didn't have any data transfer capability. So 2.5G, as we know, is basically GPRS, okay, General Packet Radio Service. And 8G is actually referred as 2.75G, okay, enhanced data rates for global evolution or GSM evolution. So, and then we had the 3G, which is again, there was a change in the way which we modulate the signal. 3G was totally CDMA. 2G had both CDMA and normal FDD kind of modulation, CDMA, FDD kind of modulation. And then 4G again changed everything. We don't use CDMA in 4G. The modulation scheme is different, and it is enhanced 3G speed and the interoperability protocol, high speed and IP based. It's totally IP based, and so you get much more data rates in 4G. So these are the things. So few more specifications. These are the basics. We will not, we won't get this in exam, I think, because the syllabus starts from this point. Okay, key enablers for LTE features. So there are 5 main features, 5 enablers for LTE. So first and foremost, it is the OFDM. Second thing is the altered version of OFDM, which is the SC-FDMA and SC-FDE. And third one is the channel dependent multi-user resource scheduling. Fourth one is multi-antenna techniques. And the last one is the IP-based flat network architecture. So in exam, what you can expect is you may get a question on, write a short note on key enablers for LTE features. So if you get that question for 10 marks, so just list out these 5 things and write 2 or 3 lines about it. Okay, or just a bit more about OFDM. Okay, we'll see in the next level. But I think what kind of question you'll get is, you'll get question like explain the advantages of OFDM or something related to OFDM in depth. SC-FDMA, I don't think in this first module in this. Okay, even the channel dependent multi-user resource scheduling is not a big topic to explain. Maybe 3 or 4 marks question. You may get a question on multi-antenna techniques because you have multiple techniques inside that. So 4 techniques. So you may expect a question for 10 marks or 8 marks on multi-antenna techniques. And then last one, IP-based flat network architecture, another important question that you may expect in final exam. Okay, so these are the main things. So coming to this first feature, which is enabler, which is OFDM. So the key difference between existing 3G systems and LTE is the use of OFDM, orthogonal frequency division multiplexing, because 3G used CDMA, WCDMA. But OFDM changed all that. We go for entirely new kind of waves, wave shape or modulation scheme to transmit. So CDMA performs remarkably well for low data rate and voice, even if the distance is greater signal strength is low, even in that situation CDMA will perform better because it's basically spread spectrum, and even if the signal is below the noise floor, it will work excellently. But where it fails is it cannot deliver the data rates that you get to expect with the modern systems. So that is the major drawback of CDMA. So this OFDMA changed all that. So some of the advantages of OFDM which led to its selection. So these things, these things are second modular things. So the idea in OFDM is you have a data stream, serial data, and you perform modulation. So QPSK means one symbol will have 2 bits, and 16 means one symbol will have 4 bits, and so on. And you do the parallel encoding and then transmit. So this is one more figure. Okay, serial to parallel conversion, constellation mapping, and perform FFT inverse, and then digital to analog conversion, add all the waves, and then you have the final baseband signal ready for transmission. So this is another, just for understanding, I put this image. Orthogonal spaced overlapping subcarriers. The advantage with this OFDM is, if you check their frequency spectrum, independent subcarriers overlap with each other. The spectrum overlaps, but because they are orthogonal, it won't cause any trouble while demodulating. So it won't cause any distortion. That is the advantage of OFDM. Okay. So these things just for understanding I put. Okay. So in frequency view, time view, how it is, how you can visualize it. So basically, as you know, square wave in time domain will result in that sync wave in frequency domain. That is what we are visualizing. So guard intervals and symbols are there, and frequency domain view on x-axis, and in time axis is there, z-axis basically. So that is the symbols. You can see it's a square pulse, and this FFT is always sync pulse, and these sync pulses are overlapping in nature, but they won't cause any disturbance. And this is one more aspect of wireless communication, multi-path interference. So when you transmit a signal from mobile or vice versa, you may not have line of sight. So the signal will hit the object and will reach the mobile phone. And it will undergo scattering also, shadowing also. There will be path loss because as the distance increases, signal strength reduces. That is called path loss, simple term to understand. Okay, and diffraction is there, reflection is there. So on this signal in this mobile phone will make same signal will arrive in multiple paths, and those paths will have some delay associated with it. But the problem with those multiple paths is it will cause interference. It can be either constructive or destructive. But all in all, it's an effect that we don't want, and we should have a mechanism in which to choose the best one. Okay, that is what our design should be, to choose the best path and reject the multi-path interference. Okay, so this OFDM provides elegant solution to multi-path interference. Okay, so when the time delay between the various signal paths is significant, fraction of the transmitted signal symbol period or transmitted symbol may arrive at the receiver during next symbol and cause ISI, inter-symbol interference. Okay. At high data rates, the symbol time is shorter, hence it only takes a small delay to cause ISI, making it a bigger challenge for broadband wireless signal. So to address this signal where at high data rate, symbol time is shorter and symbol time itself is shorter. So this even if there is a small delay in the multipath component, it will cause a lot of trouble. So in order to mitigate this, what we can do is in OFDM, we are using multiple subcarriers. So you can send a bit lower data rate in multiple paths, okay, to counter this multipath interference. Okay, OFDM is a multi-carrier modulation technique that overcomes this challenge in an elegant manner. So basic idea here is multi-carrier modulation is to divide a given high bitrate data stream into several parallel low bitrate streams and modulate each stream on separate carriers, often called as subcarriers or tones. So splitting the data stream into many parallel streams increases the symbol duration of each stream. So here is the keyword, increases the symbol duration of each stream such that multipath delay spread is only small fraction of the symbol duration. So we can easily counter the multipath interference. OFDM is a spectrally efficient version of multi-carrier modulation where subcarriers are selected such that they are all orthogonal to each other and they are all overlapping with each other. So spectrally efficient. So this term is important, spectrally efficient. That means, so normal modulation, what we do is normal transmission. We want to make sure that there is enough gap between two frequency bands. That's what we do in FDMA. Right, FDMA means there is a gap between two frequency bands. But in OFDMA, there is no gap, it's overlapping with each other, but this overlapping doesn't cause any trouble because they are orthogonal with each other. We can easily segregate the signal at the receiver. So this is advantage, first advantage. Next, so basically what happens here is by making the guard interval larger than the expected multipath delay spread, ISI can be completely eliminated. So adding a guard interval, however, implies power wastage and a decrease in bandwidth efficiency. This is one drawback. If bandwidth efficiency will be decreased and power wastage will be more in OFDM. Okay, we'll come back to this topic later. So these are the things we should keep in mind. Next is OFDM reduces computational complexity because we just use a fast Fourier transform to implement it, and the computational requirements grow only slightly faster than linearly with the data rate of bandwidth. Just you know the advantage of FFT. It's an algorithm which speeds up the process of calculating DFT. So so we implement this OFDM using the FFT concept. Next advantage is graceful degradation of performance under excess delay. So what happens here is performance of an OFDM system degrades gracefully as the delay spread exceeds the value designed for. Greater coding and low constellation size can be used to provide fallback rates that are significantly more robust against delay spread. So in other words, basically what it means is OFDM is well suited for adaptive modulation and coding, which allows the system to make the best of the available channel condition. That means one fellow is having a good connectivity, like his home is in a city and tower is quite visible from his home, or like the line of path is visible. That means it's like he's getting a good network and he can be given high data rates. So higher constellation like 64 QAM can be used to transmit 6 bits of data per symbol is transmitted. So he will get maximum maybe 24 Mbps in a LTE network. He will get, okay. If no one is there, maybe up to 100 Mbps. But someone who is living in a remote area and a hilly area, he may not get full 5-bar signal, means 4 network bars in his mobile phone. That means 1 or 2 bars on his mobile phone. You can see coverage is weak. That means you cannot go for 64 PAM. That will cause delay. Okay, and the reception won't be proper, and if you start streaming, no, it's not possible because there will be lots of error happening and phone will struggle to correct those things. So in those scenarios, the network will fall back to a safer bit rate, like it will fall back to QPSK or 8PSK. So that just 2 bits per symbol will be sent, and data rate will fall significantly. So that is the concept with OFDM. Okay, that you can do. Next is exploitation of frequency diversity. As you know, we are using coding and interleaving across subcarriers in the frequency domain in OFDM. So if there is a burst error happening and you lose significant amount of transmitted data in air, then it can be reconstructed effectively in OFDM because only some part of the spectrum gets affected, other parts remains the same. And also, see, I'll tell you here. So I'll just observe this. So we are transmitting the data 0, 0, 0, 4 ones and again 0. And there's a burst error happening because of lightning or some other environmental conditions or interference. These 4 ones are basically getting lost. Okay, so what we can do is we can write it in columns and read it through rows so that we are spreading the burst error in between the proper signals so that our error correction codes can handle the errors. Like if there are 4 error bits arriving at the receiver at once, then it's difficult to recover what's happening. Okay, but if you mix those 4 bits with the proper bits in between, like this shuffling and all, then out of 3 bits or out of 10 bits, 2 bits can be corrected, suppose. Okay, then in that scenario, you can easily correct the burst errors. So for GSM, even if you miss around 200 bits together, it can easily correct. And LTE is more advanced. Okay, we are using more advanced correction algorithms or error correction codes to correct these kind of errors. So this is fast data we are transmitting. You can see that cyan colored bits data packet is undergoing burst error. So what we do is we just interleave them. So cyan is interleaved. You can see blue, cyan, green, yellow in the second row. Okay, so this is what I mean by interleaving. So if you send it as it is blue and then cyan and then green and then yellow, if there is a burst error, I am losing 3 bits of this cyan and I may not be able to reconstruct it. But if I go for interleaving, I am just mixing the signal. So blue, so I'm taking 1, 1, 1, 1, 1 from each color and mixing it up and transmitting. And because there is a burst error, I'm just losing 1 bit of blue, 1 packet of blue and cyan and then green, and then it fits in middle of those colored packets, so it can be easily recovered. So that is the concept in we use in interleaving. So another advantage is enables efficient multi-access schemes. So partitioning different subcarriers among multiple users we can do. Anyway, we have multiple subcarriers and we can assign them to multiple users. This scheme is referred to as CDMA and exploited OFDMA and exploited in LTE. OFDMA offers the ability to provide fine granularity in channel allocation, which can be exploited to achieve significant capacity improvements, particularly in slow time varying channels. Okay, we can increase the system capacity by using this scheme. Next, it is robust against narrowband interference. It's relatively robust against narrowband interference since such interference affects only a fraction of the subcarriers. Like your bandwidth is suppose if it is 20 megahertz, and 20 megahertz means in real sense maybe like 1020 megahertz to 1040 megahertz. So if there is a frequency selective fading happening. So maybe a particular band is getting affected, like 1022 band is getting affected. So only that particular band will suffer. The remaining will be intact. So that is the advantage with this OFDM. So robust again, narrow band interference, and suitable for coherent demodulation because it is relatively easy to do pilot-based channel estimation in OFDM systems, which renders them suitable for coherent demodulation schemes that are more power efficient. So pilot-based channel estimation is you just send a pilot signal which whose characteristics the receiver is aware of. Like you send a initially known signal to the mobile phone, and when the mobile phone gets the signal, because it knows what was sent, it can assess the channel condition and use the coherent demodulation effectively. So that is the advantage with this. Next one is facilitates use of MIMO. So MIMO, as you know, it stands for multiple input, multiple output, and the channel has to be flat. MIMO techniques to be effective, it is required that the channel conditions are such that multi-part delays do not cause inter-symbol interference. Okay, so so if you want the MIMO techniques to be effective, the channel conditions and multi-part delays should not cause inter-symbol interference. Okay, channel has to be flat fading channel and not a frequency selective one. Means all the things are faded equally. That is the concept. That is the thing we want. So at very high data rates, this is important. Just remember this. This is not the case, and therefore MIMO techniques do not work well in traditional broadband channels. Okay. So at high data rates, fading will happen. So as you increase the frequency, the fading will be more, and it is very difficult to handle. I mean, work with that high frequency to correct the receive the data effectively, because it will undergo lots of fading and all. So OFDM, however, converts a frequency selective broadband channel into several narrowband flat fading channels where the MIMO models and techniques work well, because we are using parallel stream of subcarriers of lower data rate compared to traditional way of CDMA, where we are using high data rate transmission. Here we are using low data rate parallel transmission. So overall, we are sending more data with less trouble. So okay, that is the advantage with OFDM. Efficient support for broadcast services. Broadcast is as you know, one output, multiple receivers. So here, what we can do with OFDM is we can synchronize the base stations. Like we have multiple towers located in Benjanpadal or in BC Road or Mangalore, several areas. Suppose if some mobile phone is there and we want to increase its signal strength or enhance that signal strength, suppose in a center of the city. So, and that mobile is not getting proper networks. What we can do is we can use the SFN, single frequency network, like multiple towers will switch into a particular frequency and transmit the same signal. Okay, so that is the concept here. This allows broadcast signals from different cells to combine over the air to significantly enhance the received signal power, which basically enables higher data rate broadcast transmission for a given transmit power. So LTE design leverages this OFDM capability to improve efficient broadcast services. So this is one advantage. So along with that, we have some disadvantages, and the major disadvantage we discussed about it in the class. So which is it is having high peak to average ratio, PA or PAPR, peak to average, peak to peak, peak to average power ratio of PAPR, just you can say PAR. which causes non-linearities and clipping distortion when passed through an RF amplifier. So all these things come down to our basic amplifier design. So you need to operate it in a linear zone, if you remember from power electronics or AEC. So power amplifier should be operated in the linear zone. Transistor Q point should be located in the linear point, right? So operating point. So if you have this variation, it may go beyond that linear, and it will cause non-linear distortion. Okay, so that we don't want. So that is the problem with OFDM. Mitigating this problem requires the use of expensive and inefficient power amplifiers with high requirements on linearity, which increases the cost of the transmitter and is wasteful of power. So, so all in all, the idea here is to mitigate those problems and all, you need to invest a lot of money. Means equipment will be costly, and it basically wastes the power also. And this technique is not ideal for uplink, that is mobile phone. So you can use this only in the downlink. Mobile tower or the base station can use this OFDM, but for a mobile user, mobile phone, this will be very inefficient. It will be very power hungry, and it will drain the battery very quickly. So we don't go for this OFDM in the uplink. So mobile phones don't use it in the uplink. They don't do it, but they can only receive the OFDM signal which is sent by the mobile tower. Okay, so this is the major thing, and you should always remember this drawback of OFDM, which is high PAR, and the remedy for that is to go for SC-FDMA, a single carrier frequency division multiple access thing, which mitigates this problem. So here, and the second thing is the SC-FDE and SC-FDMA to keep the cost down and battery life of LTE incorporated power efficient transmission scheme, which is the SC-FDE. So SC-FDE is conceptually similar to OFDM, but instead of transmitting the inverse force IFFT of actual data symbols, the data symbols are sent as sequence of planned symbols with cyclic prefix added. Okay, so this is the difference. The IFFT is added at the end of the transmitter, and these signals have low PAR of 4 to 5 dB compared to OFDM. Uplink of LTE implements a multi-user version of SC-FDE. Okay, multi-user version of SC-FDE, single carrier frequency division equalization, is called as SC-FDMA, which allows multiple users to use parts of the frequency spectrum, not the entire spectrum. Just part of the spectrum is used by a particular user. And SC-FDMA closely resembles OFDMA and can in fact be thought of as DFT pre-coded OFDMA. That's it. That is the basic idea behind it. DFT pre-coded OFDMA results in SC-FDMA. Okay. SC-FDMA also preserves the PAR properties of SC-FDE, but increases the complexity of the transmitter and the receiver. Yes, so these are the first two topics. Third one is the channel dependent multi-user resource scheduling. So OFDMA provides enormous flexibility in how channel resources are allocated. So OFDMA allows for allocation in both time and frequency, and it is possible to design algorithms to allocate resources in a flexible and dynamic manner to meet arbitrary throughput delay and other requirements. Okay, so if you remember in the class, we studied that LTE resource grid. So basically it has both time and frequency allocation. Okay, we can flexibly allocate them and make the system efficient. Okay, the standard supports dynamic channel dependent scheduling to enhance overall system. So you can allocate more resource to the needy person, like if someone is streaming a movie or something, he should get the data required. And if someone is just talking, he doesn't get that much of bandwidth or resources, or some phone is idle, you need not allocate any resource to that mobile phone, because it's in idle state. It's neither transmitting or receiving any data or even call. So you can save on the bandwidth and you can use it, utilize it some other fellow. So this is what channel dependent multi-user resource scheduling is. So given that each user will be experience uncorrelated fading channels, it is possible to allocate sub-carriers among users in such a way that the overall system capacity is increased, just like I explained. This technique is called frequency selective multi-user scheduling. Calls for focusing transmission power in each user's best channel portion, thereby increasing the overall capacity. Frequency selective scheduling requires good channel tracking and is generally only viable in slow varying channels. For fast varying channels, the overhead involved in doing this negates the potential capacity gains. So if the slow varying is like if you're sitting idle and everything is like channel, you're getting a good channel, that is fine, you can do all these things. But if you are moving, then the channel is fast varying, like the link connectivity, link parameter, everything is changing dynamically and very quickly. So it causes lots of overheads, and it's difficult to uh, get any gains from that, or system gains. Anyway, it's a burden on the system also. You need to track that person, measure the channel all the time, talk to the neighboring cells to make them measure it and to hand off if required. So these are the things which we need to consider practically. Okay, so same thing. So I can skip this. Yeah, next one. So this is important multi-antenna techniques. So LTE standard provides extensive support for implementing advanced multi-antenna solutions to improve link robustness, system capacity, and spectral efficiency. So depending on the deployment scenario, one or more of the techniques given below can be used. So 4 techniques that is used in LTE are transmit diversity, beamforming, spatial multiplexing, and multi-user MIMO. So transmit diversity, it's basically used to combat the multi-path fading in wireless channels. The idea is basically send copies of the same signal but coded differently. So this is the important thing, coded differently. Second, yeah, coded differently over multiple transmit antennas. LTE transmit diversity is based on space frequency block coding, SFBC techniques complemented with frequency shift time diversity, FSTD, when 4 transmit antennas are used. And the transmit diversity is primarily intended for common downlink channels that cannot make use of channel dependent scheduling. And it can also be applied to user transmissions such as low data rate VoIP. Transmit diversity, see, important thing, last line, diversity increases system capacity and cell range. Okay, cell range is increased and system capacity is also increased. So this is the thing, we are sending the same data, okay, but encoded differently using multiple antennas. 2 transmit antennas are shown here, transmit antenna 1 and transmit antenna 2. So this is SFPC. Next one is beamforming. So here the idea is, okay, I'll show, yeah. So antenna means this is not a single antenna element. We will have n number of antenna elements, basically array of antenna here, and we just control the power given to each antenna to shape a beam in particular direction. So what we can do is we can use the same frequency to connect to different users, because we are transmitting signals in different paths, different beams like this. So this phone gets the beam from signal from this beam, and this one from the bottom beam. So this is the idea with the beamforming. Beamforming can provide significant improvements in coverage, range, capacity, reliability, and battery life. It can also be useful in providing angular information for user tracking. LTE supports beamforming in the downlink. Uplink, your mobile phone is not that much capable. You need an array of antenna to do that. So mobile tower can do that. And this is helpful in see this line, user tracking. So tracking means you are if you're using Gmap and all, it will say even if you're not using GPS, your mobile tower can tell which direction, which place you are residing. Okay, just observe next time. So sometimes it says you are in this particular circle, or sometimes it will say in this direction. Okay, you might be aware of the tower location because it is connecting you to some sectoral antennas. It can tell which direction you are compare or in with respect to a particular mobile tower. Okay, that information you can track more efficiently with the beamforming. So four antenna array, and this is just a illustration. So what you can do with beamforming. So interference can be avoided because you can beam the signal towards a particular mobile phone easily in this. Okay, so another example is given. Next is spatial multiplexing. Okay, so another technique of another multi-antenna technique. So idea behind spatial multiplexing is that multiple independent streams can be transmitted in parallel over multiple antennas and can be separated at the receiver using multiple receive chains through appropriate signal processing. And this can be done as long as the multiple channels as seen by the different antennas are sufficiently decorrelated, as would be the case in a scattering bridge channel. And it basically improves provides better data rate and capacity gains. Okay, so this is the idea here. Multiple spatial diversity. Just select the strongest signal. So you use a multiple receiving antenna here, and it gets the signals. Both antennas get signals, multiple signals, reflected, diffracted, multiple versions it will get. Now, what you can do is, because of this spatial diversity, space is actual space, physical distance here. Each channel will be uncorrelated, means the signal received by first antenna is different from the signal received by the second antenna. Now, just make a choice which one is better and reject the other one. So, this is spatial diversity. And another thing is multi-user MIMO. This we will discuss in depth later chapters. Okay, it is currently not supported in the uplink because uplink is from your mobile phone to mobile tower because of complexity and cost considerations. However, multi-user MIMO, which allows multiple users in the uplink, each with a single antenna to transmit frequency and time resources supported. Okay, so this is the multi-user MIMO is shown here. So multiple antennas, multiple users are there. Okay, and you can split the stream accordingly. You can provide one stream, single user MIMO. Just all the streams are transmitted to one user, but in multi-user MIMO, you can split the stream to provide a particular connectivity, a particular what you call data speed to the to multiple users. And this is how it looks like. If you look at mobile towers, you will see multiple antennas, and that is basically for spatial multiplexing. Yeah, another example, E-node B, spatial multiplexing, and for a better spectral efficiency. Last one of the key enablers is IP-based flat network architecture. Besides the air interface, the other radical approach of aspect of LTE is the flat radio and core network architecture. And flat means fewer nodes and a less hierarchical architecture, and low cost and lower latency requirements. So all these are the advantages. It's basically IP based. That is the keyword here. IP based flat network architecture. Just you can create a LTE E node B, means transmitter in your home. Means if you have the all the protocols, uh, software with you and the permission, just connect it through LAN cable. It will be ready. It's basically IP based. It is so easy. Okay, now we'll see what it means, flat architecture. So SAE means system architecture evolution, SAE architecture. Now 2G to 3G release 6, we had this GGSN, which is gateway GPRS service node, which connects to SGSN, which is serving GPRS service node, and which connected to BSC or RNC, radio network controller, and then to base station transceiver system, which is the mobile tower. This was the traditional way of connection. Now, in the HSPA, high speed packet access, release 7, direct tunnel option. So this GGSN straight away connected to RNC, bypassing the SGSN using the direct tunnel option, and that connected to node B. That is the terminology we used in node B is the terminology we used in 3G networks, and BTS was for 2G. Okay. Now here there's a one node reduction. Okay. Now coming to release 7, node B with RNC function. So here we have this system architecture evolution gateway, and it connects right away to node B with the RNC functionality. So BTS translated into this node B with RNC connection. But here in the third version, we have this node B with RNC block. Okay, RNC block merged with node B here. So there's a reduction of one block here, one node, and SGSN is there, and that can be bypassed. In the last version, SAE gateway, this is what we have in 3G LTE release 8 and in LTE network. So gateway straight away connects to E node B, and there is only one MME, mobility management entity. So this is the simple architecture. That's what we call flat LTE SAE architecture. Compared to the first one, and you can see how much reduction here has been seen. And what is the advantage with this is the latency associated with each node is eliminated straight away, and the latency is a vital thing for streaming application. And if you are having a video conference and all, you just expect it to reach immediately. You don't want any latency. So this is really useful. Okay, and that is the advantage, main advantage of LTE SAE architecture. So this one, I think you can go through the functionalities. Explanation, same thing I explained. Now, next topic is LTE network architecture with the evolved packet core architecture. Yeah. Are you there still?
Yes, sir.
How many are there now? I cannot chat.
32, sir.
32. Okay. Fine. So I think another 10 minutes enough, right? 1 hour. What do you think?
Yes, sir. 1 hour is enough.
Okay. Am I going fast or enough? Shall I? What should I do? So this is the EPC architecture, and this architecture is developed so that you can have backward compatibility with the existing 2G and 3G networks, and you can see it here. So if I zoom in, so GSM, GRAN, UMTS, so GSM, GRAN is the 2G network, and UMTN, HSPA is the 3G network. LTE is basically 4G, as you know, and other access technologies, WiMAX and all. and CDMA is another version of 2G. Okay, so if you remember that Reliance, Tata Indicom or Reliance, that was basically 2G CDMA network. Okay, around 10 or 15 years ago, that was used. That was there 10 years ago, I think. And then you had another version of 2G. Okay, in 2G we had two ways, two types, GSM and CDMA. And then 3G changed all that. 3G was purely CDMA, uh, WCDMA. Okay, so kind of unified it. And LTE, there's only one standard throughout the world now. Okay, LTE means, LTE phone means it can work in a specific band. All the architecture, everything is same, and future generations will have same architecture, no ambiguity when you develop a mobile phone or something. And the issue with the first generation mobile phone was Europe had its own technology. In Europe, UK had its own technology, Japan had its own technology, and US had its own technology, and India didn't have any mobile means in the first generation. So unifying them was a difficult task. Means the mobile phone which works in US may not work in Europe because the frequency of operation band was different. And when we had 2G, again there were two types of architecture. Okay, one was GSM, another was CDMA. CDMA phone will not work with GSM, and when we had that CDMA here, you cannot get the same. The phone you need to buy it from the mobile service provider. That is still the case in US actually. You have to purchase from the mobile service provider. Okay, so that was the thing. Now, so GSM connected to SGSN, SGSN connected to management, mobility management entity, and that connected to serving gateway. And you have this one tunnel option, which we saw in the previous block diagram. So that connects to HSPA or UTRAN network. And then you can see the difference here. So for eNode B to serving gateway, straight away there is uh, no other node present in middle. Okay, straight connection. One parallel path is MME to track the movement and all. Okay, and other thing is CDMA connect. CDMA, you need a PDSN for CDMA, which works similarly to SGSN network, SGSN node, and then you have PDN gateway to other access technologies, and PDN connects to the IP services or any other connectivity you want. So mobile network like Airtel has all these things involved. Geo doesn't have all the other things. Just LTE eNode B is there with the Geo network. For Airtel or Vodafone or BSNL, I think if they introduce 4G, they have to go with this kind of architecture. So backward compatibility with the existing users of 2G and 3G, and then you provide connectivity to the internet and all other access technologies. Okay. Now you have this PCRF, which is what you call policy and charging rules function, which keeps track of how much you should be charged and what is the policy. All those regulations and policy of the company and the government, everything is put as algorithm there. That entity will manage that. Okay, so these are the blocks involved in EPC, and this question you can expect in exam. This one and the previous one, this one. So don't get confused. This is a 3GPP evolution towards a flat LTE SAE architecture. Okay, so just you're showing the evolution from two nodes in between to no node in between. Okay, in the last figure. So this is evolution. You need to explain with the block diagram, and this one is EPC. And see, just don't mess up with the full form and the connectivity here. Okay, explanation. Okay, fine. You write it on your own, and most of the times, okay, no one is going through your write up actually in depth. What you write here, what you show in figure is the main thing. Okay, if there is a figure in question, so don't mess up the full form and the connectivity. Okay, so it's quite simple. LTE has direct connectivity from serving gateway, and there's a bypass through MME, and GSM connects to SGSN, and even HSPA connect to SGSN, but HSPA has a one tunnel option through serving gateway that you just show, and CDMA connects through the PDSN, and there's other access technology connecting to PDN gateway, and then PDN gateway connects to PCRF and IP IP services. Okay, so these things you remember. Okay, so this explanation. Now, another important concept is the cellular concept. So, the basic idea here is, if you just take the example of Mangalore city, if you put a one tower in the middle of Mangalore city, like in a State Bank area, and put a high power mobile tower, and you try to connect with the people with a given spectrum, the scope of putting users is more users is limited, because with a given bandwidth, suppose if the bandwidth is 1 megahertz, and each user takes 100 mega, if the bandwidth is 100 megahertz, and if each user takes 1 megahertz of bandwidth, you can put a maximum of 100 users. If you're not using any control channel, any bandwidth for control, you use a different channel for controlling, then you can put maximum of 100 users. So that is the drawback with the single tower wide area mobile network theory, which was the first thing implemented in Stockholm. Now people realize that is not efficient way of using the given spectrum, because it is very costly and very scarce. Okay, spectrum is limited. So just divide the area into smaller cells with a smaller mobile tower with low output power, so that you can cover more people. So within that 100 megahertz range, you can put 1,000 or lakhs of people if you put smaller low power mobile towers with smaller range. Okay, and if you just manage the things so that you don't cause any interference, then it will work very efficiently. Okay, that is the idea here, cellular concept. Okay, so that thing is explained here. So this is what we do here, the reuse of the same frequency, and see here we are using the same the bandwidth is split into 7 different cells, and we can reuse the frequency in another cell. So just for example, now I have the if I have the what do you call bandwidth of 700 megahertz, I'll divide 700 into 7 equal bandwidth part. So each cell A to G will get 100 megahertz each. So in total I have 700 megahertz bandwidth, right? Now here while I place this, so this band 1 to 0 to 100 megahertz, 100 to 200, 200 to 300, 300 to 400, so on. So all in all, with this one dark layered cell, I can cover 700 megahertz. Now, as I'm splitting them into 7 equal bands, I cannot put the same frequency cell in the neighborhood. So C cannot be a neighbor to another C. One C is here, okay, and another C is here far away. Okay, so that I'm planning my layout so that there is no interference from the same frequency. This is the main idea behind cellular concept. So I can split the spectrum into multiple clusters, and then I can put, okay, can use that. So cellular systems allow the overall system capacity to increase by simply making the cells smaller and turning down the power. In this manner, cellular systems have a very desirable scaling property. More capacity can be supplied by installing more base stations. As the cell size decreases, transmit power of each base station also decreases correspondingly. And see, the thing here is, as you reduce the cell size, basically the mobile tower is radiating at a less power. It is good for the people living around. Plus, your mobile phone doesn't have to reach out to a long distance. Cell tower is located nearby. Even your mobile phone has to send signals at a lower power level, and it will save the battery. Okay, so if you noted in city area, if the connectivity is good, the battery drains lot less compared to village area, or if you are traveling, even if you're not talking, or if your phone even if your phone is idle, it will drain the battery quickly because it is constantly connecting with the mobile towers, and it is at a greater distance. It needs to emit signal at a higher power level, so it will drain the battery. So this is the advantage of cellular network. Cellular systems also support user mobility, means when you move from one area to another area, you need to connect to a different mobile tower. So you need to be handed off to a new tower. Your mobile phone, even if it is in call or streaming, there should not be any disruption of services. Smooth transition should take place, and uh, handoff process should be done, okay, in order to facilitate that. So achieving smooth handoff is a challenging aspect of cellular system design. Okay, most of it's a big headache actually to shifting to transfer the call from one tower to other tower when the user is moving. There's a lots of background processing that happens. Okay, and although small cells give large capacity advantage and reduce power consumption, their primary drawbacks are the need for more base stations and the need for frequent handoffs. See, these are the drawbacks. So the problem is with this small cells is we need to implement more towers. Like in Mangalore city, you just want to put more tower in that market area and all. It's very difficult to acquire the uh, cell side. Or if it is residential area, people may not agree uh, uh, to put a cell tower there in their locality. They may object, or you may not get a place to put your mobile tower. That is one thing. And also, anyway, you need to pay the rent and all. The equipment will cost some fortune to set up. And plus, if you have smaller cells, means handoff will be frequency. Just 1 kilometer, 2 kilometer you travel, you may have to be switched 4 or 5 times into multiple towers. That is a big headache. Okay, that puts a burden on the systems. These are drawbacks, but still we go for the smaller cell because of the big advantage it provides, like saving on the bandwidth. Without going for additional spectrum, you can put more users. Okay, so analysis of cellular systems. I think I can stop it here. I can take it up next class. Okay, 1 hour. Okay, right?
Yes, sir.
Yeah, exactly 1 hour passed. Okay, only 7 people now. 30 people. Yes. What happened now?